Okay, the equation y double prime minus y equals 0 has solution set e to the t, e to the negative t, make that a set, so that your general solution would be y of t equals c1 e to the t plus c2 e to the negative t. And this is also called a fundamental set. We can check that it's a fundamental set using the methods that we've developed so far. Now let's consider the equation y double prime minus y equals t squared. As we know from the terminology we've already developed, this equation is homogeneous. This equation is non-homogeneous. For reasons that we'll see, we want to try to find just any solution to this equation. So let's try a solution. Let's try y of t equals t squared. Well, if y of t equals t squared, then y double prime is 2, and we get y double prime minus y is going to equal 2 minus t squared, which is not equal to t squared. So this doesn't work. However, we did get a t squared out of this. So we might try y of t equals negative t squared. That'll make the negative t squared here positive. We're going to get then y double prime equals minus 2 plus t squared. That's not equal to t squared, but at least we've got a plus t squared here and here. What are we going to do about this negative 2? Well, the negative 2 comes from the second derivative, and that should be y double prime minus y equals this. If we try y of t equals 2 minus t squared, or let's say even better, negative 2 minus t squared, then y double prime minus y is going to equal what? Well, y double prime is going to give us a negative 2t squared, I'm sorry, a negative 2t, a negative 2, so y double prime is negative 2, and then it's minus negative 2 minus t squared. This equals t squared. So this works. Furthermore, if we add this solution, negative 2 minus t squared, to the solution to our homogeneous equation, the solution still works. And the reason for that is fairly simple. If we run this solution through the left-hand side, we're going to get 0. If we run this solution through the left-hand side, we're going to get t squared. So if we run this plus this through the left-hand side, this part's going to give us 0, this part's going to give us t squared, and we're going to have a solution to this non-homogeneous equation. So that y of t equals c1 e to the t plus c2 e to the negative t minus 2 minus t squared is a solution to the equation y double prime minus y equals t squared. You should verify this. And having verified it, you should see very clearly how running this solution through the y double prime minus y yields t squared, and how the fact that this solution is 0, this solution gives you 0 when run through the left-hand side, and this solution gives you t squared when run through the left-hand side, guarantees that any solution of this form, no matter what C1 and C2 are, gives a solution to this equation. So we can say more generally that solution to the non-homogeneous or to the homogeneous equation gives us a solution to the non-homogeneous equation. And we can also say that sometimes the solution to the non-homogeneous equation can be found using common sense. So as not to hold you up while I write this down, I can say that every solution to the non-homogeneous equation, to this particular non-homogeneous equation, has to be of this form. Now we haven't proved that. We'll see to an extent why this is so. And there's more. An analogous statement is true for any non-homogeneous equation. What do we mean by an analogous statement? Well, the analogous statement is going to be, if we've got a solution to the homogeneous equation, and we can get any solution to the non-homogeneous equation, we can add them together and get the form of every possible solution to the non-homogeneous equation. We can summarize that statement, and we're going to introduce a little terminology. Y sub c of t is going to be our solution to the homogeneous equation. That just corresponds to our general solution up here. Y p of t will be any solution to the non-homogeneous equation, and maybe we'll put the word any in there. And right here is a solution to the non-homogeneous equation. We call the solution to the homogeneous equation the characteristic solution, and we call the homogeneous equation here the characteristic equation for the non-homogeneous equation. Okay? And y sub p is just any old solution to the non-homogeneous equation. We call that the particular solution. And then we can make the statement that the general solution to the non-homogeneous equation is the sum of the characteristic and the particular solution, the sum of the solution to the homogeneous equation and any solution to the non-homogeneous equation. And we can make one more statement, that is that two particular solutions differ by a solution to the homogeneous equation. If we subtract one particular solution from another, the difference is going to be a solution to the homogeneous equation. It's going to be some form of our characteristic solution for a couple of specific constants. Now the question that can arise is, how do we find a particular solution to a given equation? For example, if we have the equation ay double prime plus by prime plus cy equals t squared, how do we know that the solution should be some combination of powers of t? Or if we have a cosine of t, what kind of y functions would we put into our equation in order to end up with a cosine? We'll go on with this question in the next clip.